I'm going to share for the next, hopefully hour and a bit maybe, a little bit on background to computer vision, a little bit on how it works. So it's going to get a little bit hairy at some points, but don't worry, it's not too much math. It's more of the fundamental concepts which I want to cover and understand, give you that understanding of how it works, and then move on towards how do you actually build these things and how do you test them, because there's a lot of discussion about what is computer vision, these applications, but no one actually tells you, okay, so you build it, but how do you use it and how do you compare it? And then move towards using computer vision on AWS and how do you build that. And then finally, if we get time, we'll cover a use case which I've been building, which looks at a specific kind of case, which is all around how do you help insurance companies with their claims by using technologies like computer vision. And that there's a code base for that, and there's a great example hopefully you guys will like. And it uses a variety of different AWS services to get this working. But let's see if we get to that point. So like I said, to start with, I want to give you a bit of a background and some fundamental kind of pillars that computer vision is based on. And just to kick things off, I'm not sure if you've all seen this before, but this is the goal of, this is one of the goals. There's many goals in computer vision from many different stakeholders and perspectives, from a researcher, from an, implementation perspective, and from the business, perspective. But let's just say the ultimate goal for computer scientists and computer vision is to be able to detect objects, or be able to detect, some concept within an image, and whether that be just classifying whether it's a dog or it's a cat, or whether it's doing segmentation in an image and being able to detect objects at certain locations, or even more more advanced techniques like segmentation and layering, so you can start to build metadata around an image. How many cars are in it, who are they interacting with, and how are they interacting? So you start building semantics around these. So you have these various different tasks, but the ability to do that is quite difficult, because computers obviously do not understand images, they only understand numbers. So I'm going to go and step back slightly and just take a second and think about this, because what we're going to be talking today, when we talk about computer vision, I'm going to be framing it in the context of neural networks. Now, I am not one for buzzwords, and I'm not one to follow the hype. If anyone knows me or gets to know me, they'll know I am very much a traditionalist when it comes to doing anything to do with machine learning. I believe the simple method works the best. However, in recent years, we will see that computer vision is really supported and made possible with the advancements in large data stores, high compute power, and the use of neural networks. So I just want to give you a quick fundamental understanding of what a neural network is, because that will then help you frame and understand how computer vision architecture, these things called neural networks, convolutional neural networks, can work. So at the very fundamental basis, that kind of the smallest unit of work that actually is possible with a neural network is this thing called the neuron. And the neuron, as you can see on the slide, hopefully everyone can still see the slides, has a bunch of inputs. We'll call those X's, and has some bias or some weights. We don't need to worry about that at the second, which will represent on this image as +1. And where the circle is, that orange circle, we'll call that the neuron or the node. And inside that is some form of activation function. And that activation function we'll cover in a bit. And effectively, all it does is saying, depending on those inputs and the activation function, we'll have an output. And so what it could be is that activation function could be just summing up all those inputs and converting it into a percentage. Or it could be doing something else. And depending on how that activation function works, the output, which is HWB, will change. Okay, that's basically the fundamental building block for any neural network. And you need to keep that in mind, that what's important here is that those inputs, what effectively we need to do is always add them up to a value, or represent them as a value which can become an output. That's the fundamental building block. So what does that mean for a neural network? Well, if we have many, lots and lots of these little neurons, these nodes, and we join them all together, we don't have to join all the inputs and outputs together. We'll get to that in a bit. But we start to build layers of neural network or layers of neurons, which become our neural network architecture. And to do this, I've given you some wordings on the right, but effectively, when we start off the neural network, we initialize those weights. So we initialize those plus ones, which you saw on the previous slide, those biases, and we give some inputs. And in the case of our use case of computer vision in a bit, we're going to see those inputs may be numbers, which represents the color of a pixel or the location of a pixel. And for those that are kind of familiar with machine learning terms, they're effectively our features. And those inputs that go into X1 then go to the next layer, which have changed because of some activation function. And then once it goes all the way through to the very end, layer L3, that becomes your output. And as through that process, which I've just described, we are starting to train a neural network. So we've gone from a bunch of input images. And while you might be a little bit confused, I just want to keep everyone's attention here. Don't worry, I'm going to contextualize this in a minute, but I need you to understand this structure of left to right, the flow. So we've gone from a bunch of numbers, which have gone through a number of activation functions, and we have a single output. And that single output, which we're going to talk about in a minute, that layer L3, is a numerical, potentially one or multiple numerical numbers, which represents something to do with the data that we're providing. So if you're familiar with machine learning, and I don't want to go into too much into the background of machine learning, but there are many different types of machine learning. And one of them, and we're going to concentrate on today, is supervised machine learning, which means the data that we have labels about what is correct, or in our case, we're doing classification. What is the correct value, the ground truth, and what is incorrect? So, for instance, if we know that 10 different features of a certain characteristics of a row result in the label being true, or those another 10 characteristics are false, those true and false becomes our labels. So if we know those labels, we know then when we train this network, when we go forward, we know if we put the values of x1 to xn all the way through, and we get an output, which let's just say the output is true or false, and it does not correspond to the known value, which is true or false, then we're doing something wrong or we're doing something right, okay? So this process is known as the forward pass or forward propagation. And then based on whether those inputs and the activations were correct or incorrect, resulting in the right answer, we then apply this thing called a cost function. And the cost function, anyone's done machine learning, I know, Rick, you did a lot of work in optimization, so you'll have a lot of knowledge about cost functions and optimizations around cost functions. But effectively, our cost function will tell us how far away we are from that true answer. We may be, in the first instance, very unlikely, but we may be 100% correct across all of our predictions. And then our cost function doesn't need to, or our network doesn't really need to retrain. The likelihood of that happening is very, very slim. You can probably do a proof on that one and work out it's probably in the chances of the trillions, especially with bigger networks. But effectively, what we need to do is look at the delta between what we've predicted and what the actuals are. And based on that, we do this next step called backpropagation, is where we go in for each of these nodes and we start to readjust each of the weights of the nodes. So there's those weightings which I mentioned before, to adjust it to minimize the cost function or minimize the error within that cost function, assuming that we're doing some mean square error or we're doing some sum of square errors optimization. So there are different techniques, not to worry about that too much, but what I want you to kind of abstract away here is that there is a process of going from inputs all the way to an output, to comparing the outputs or the actual values, and then depending on how those values have, corresponded to the actual predictions or to the actual values, the true values, you need to readjust those weights. Now, depending on how big this network is, and how many layers there are. Right now, we're only seeing one hidden layer, that's orange layer L2. It can get very complicated and very hairy. And there is a lot of math behind the scenes to be able to do this readjustment of weights. We're going to see one in the next slide in a second, a slide, which I just put in there to give you some insight into this. But effectively, that process of going backwards requires a little bit of integration and understanding the slope of the curves. Every time you do a back propagation, we need to find out the gradients of each of your curves. So differentiate, and then you must be able to do some gradient descent on there. So it gets very complicated, but we don't need to worry about those many details. All we need to worry about is knowing that there's a forward pass, there's some weights generated on that forward pass. They are calculated with the error, and then based on that error, we recalculate the weights going backwards and restart that process all over again. So we keep doing that and keep doing that, keep doing that. So that is the fundamental basis of a neural network. The things that make it very different now, or make it a little bit of a nuance, is how do we build those activation functions? What are they, what do different activation functions do in a neural network? There's many different types, from Sigmoid, TANH, ReLU, whatever it may be, and we'll talk about those in a minute. To how do you train it to allow the different cost function optimization techniques to actually improve the network? Because sometimes you may set hyperparameters in these networks, and we're going to talk about what that word means in a minute, to incorrectly, so the network can never train. Because ultimately what we're trying to do is bring the error between what our predictions are and the actual values are together. Yeah, so we have no error. Obviously, it's a little bit more tricky than that, but we need to keep that in consideration. So moving on. Has anyone, I'm going to let everyone unmute the mic for a second. Has anyone ever seen this formula before, this function?
Convolution.
Hey, there we are. Okay, so this is just to give you an insight that it looks scary, but we're going to unpack this slightly. On the left, F star G is effectively two functions. And all a convolution means is some arbitrary function convoluted with another arbitrary function results in a new function. And we can do this at points t, which is effectively at a point in a timestamp t, or we can do it over tau. So I'm not going to go into this too much, but I just want to put this here because some people, if I'm in a face-to-face session, they love to have a discussion around this. Probably not so good if we don't have face-to-face because we can't have that interaction, but this is like the fundamental principle of a convolution. It doesn't have to be for a neural network. It can be for probability functions or mass density functions, etc. But it's just the process of bringing two functions convoluting with each other, resulting in a new function.
I think of them as sliding windows.
Yes.
Together.
Yes, there's a very nice, very good. There's a very nice example of showing how the output of the two convoluted functions, and for anyone that hasn't seen this before, and I'll try and use the details of this, the output of two functions in convolution with each other results in the output of the output of another function by showing it with two effectively rectangles overlapping with each other. It's very nice. It gives you the idea of local and maxima, which is a great way of kind of interpreting this. So let's move on to convolutional neural networks. So I'm going to give you the kind of background on this one. I say here CNNs were introduced in the early 1980s. CNNs, were being studied way before this. Neural networks were being studied early 1930s. They were conceptualizing around how do you take the human synapse or the brain synapse and model that in a way in a computational manner. Now, I don't want to go into the background of that, but effectively the premise of this the CNN was to be able to use computational techniques to use small sliding windows. We're going to call it sliding windows for now. We're going to look at what that actually means in a second, to transform an image, which is effectively numbers represented by effective different number matrices, and then use that to build up the numerical representation of that image. and from there perform different types of tasks on that image based on the patterns that we detect within those matrices. And those, remember, those numerical representations and the segments within there, they effectively are our feature space for an image. And each image has its own, magical feature space based on the depth of it, the size of it, the type of sensors or layers or effectively channels which are used in this image, which are really important to understand. So that becomes our feature map, and then we can apply a variety of different structures to that to interpret that feature map to be able to do different types of tasks. And that's important because, remember, computer vision, there's not just one type of tasks. We can do many different types of things. So at the very fundamentals of this, if anyone's seen this image before, it's the Doge. I know, and the last time I presented around this, a few people put their hands up and said, hey, I remember this. So if you do, congrats. It was a very famous image.
I never knew how to pronounce it.
Yes, the Doge. I had a researcher, colleague from MIT who used to always use this in his slides, and it always brings back good memories when I see this image. So this, I just want to give you the background. So if anyone's ever kind of unpacked a GIF or a GIF or a JPEG, you can probably see there is a numerical representation, the bit pattern or byte pattern of the image can be formed. It can form a matrix of values, okay? And each matrix of values may represent one or more channels of the image. So it might be red, blue, and green, RGB. I said it the wrong way around, sorry. But each one of those values will maybe represent the intensity of the pixel. So, how much red is in it, how much green is in it, how much blue is in it, or they may represent something else. But effectively, at the fundamental, we can represent these images as numerical matrices. And so what we need to do is find a way to go from this numerical matrices to start to build the inputs for our neural network. Remember those X1s to XNs. So what do? So they came up with this function, which is effectively a convolution, because we have an input as one function, and then we have the kernel as another, and our output is the process of convoluting the kernel over the image space, that image matrix. And all we're going to do is that we have a kernel of a certain size, and we move that kernel across the image in a kind of consistent, continuous pattern in order to build a numerical representation of a weighted numerical representation of that input matrix. Okay. As part of this, what does it look like? So I'm not going to go into the full details, but we have a kernel which is of size NN. Typically, sorry, it's black. You can't see it there, but in this case, the kernel is size 32 by 32. And the kernel is also, in this case, 3 layers or 3 depth. In that case, it effectively means we have 3 kernels working because it covers the channels of the image, red, blue, and green. So what we end up doing is that we take this kernel and we effectively move it along the matrix space of that image, those numerical representations, and we build a new representation of that image with the kernel space being the size of the output, and then on top of that, the activation function being the resulting output value that has been passed from the inputs to the outputs. And we do that repeatedly until we build our first representation of that matrix. And what we're trying to do here is turn those numerical values into some non-linearized value of the feature space. So the reason why I always ask this question face to face, and it's probably not so simple here, but maybe I'll ask it and someone can come on, off mute. What would be the problem if we didn't have a non-linear function, which was, a linear function, which was the activation function? Can anyone think of what would happen with the outputs? I'll give a few seconds before anyone doesn't answer. Oh, we got one off. No, no one?
They'd all be linearly related anyway, so.
Yes, and the output would be then the same as the inputs. Okay, so the aim of our function here, or it would be some representation of that. Our aim of our activation function is to find non-linear patterns or non-linear correlations between our inputs and our outputs, and that's the underlying premise of any activation function, is to introduce non-linearity within our network, or within our inputs and outputs. That's all it does. And we're going to look at what those look like in a minute, those type of activation functions and the reasons for them. So we've done one thing. We've now convoluted across this network space, this space, matrix space, and we've built a first hidden layer. And there are many different techniques within here, and there are many different things that you need to know about the kernel, depending on, so another question I always ask for you guys is, hey, say we have a very large kernel or we have a very small kernel, what do the differences kind of introduce into our network? Short space of time is that, hey, if we have a very large kernel, we're starting to ingest a high amount of information about our feature space. So if we have a very small kernel, we're only taking a small amount of features within each path, within each convolution. If we have a very large feature space, we introduce a lot of information at a small amount of time. So if anyone's done information theory and looked at feature engineering, they all are very related to the concept of over and under fitting. So depending on how much information is within each message, within each pass, you could potentially overfit your model because of the kernel size. But there are many different things that need to take into account of that, and a little bit of experimentation needs to take into place. But it's important to know that these kernel sizes are useful in achieving different types of tasks. And it's also important to note that depending on the type of kernel and the weights which the kernel is initialized with to begin with, those set weights, you can achieve different types of tasks. So say you have a matrix which has a certain pattern in the way that the values are formed. So effectively, you build a matrix which only has zeros and ones as their initial weights in a diagonal pattern. I'm not going to get too much of the math on this one, but if anyone's played with Photoshop and they've seen skewing or edge detection, these are actually processes which are using convolutions to do that. So if you pass over a filter over a matrix, you'll end up with the ability to do edge detection, or to be able to skew certain values within that image matrix. So there are different things you can do with this, but to begin with, it's just important to know that these kernels are the fundamental building blocks to your convolutional neural network kicking off. And they go all the way through as well, through all the layers in the network. The reason why I'm telling you these things as well, because these are the features which you need to play with and understand when you build your CNNs in SageMaker or in any computer vision scenario. So the next layer is the ability to downsample our very large feature space. So one of the things that is an important characteristic in any machine learning workflow is being able to do feature engineering in a way which reduces that feature space size down, so you don't end up overfitting to a very large pool of features. And in this case, our features are effectively parameters. If anyone's played with neural networks or done any reading on it, you can see the feature space parameter size can be extremely large, in the millions, very quickly, depending on the number of layers and the number of neurons within each of those layers. So what we try and do with the pooling layer is reduce down the feature space, or reduce down the size of our matrix which we are trying to compute with. And what it does each time, and in this case, this one is a max pooling. For instance, on the right-hand side, we see a grid which is 4 by 4, our matrix which is 4 by 4, and what we've done, we've reduced it by 2 by 2. And what this has done, if you take the first 4 boxes, which is orange, by using a max pooling layer, we take the maximum value in that first 4 boxes, and then the maximum value in those green boxes, et cetera, until you reduce with a smaller size matrix. And that allows us to compress a lot of information, but it also allows us to reduce the overhead of the model. And this is super important when you start to get to very deep models, which we'll talk about in a bit. And there's different types of pooling layers, but it's effectively, you need to know that you've gone from your inputs to a first hidden layer, which now we're going to do some certain operations to. Okay, so the next thing to think about is our fully connected layer, which is our output. And I mentioned to you at the very end of a neural network, what you need to do is have, or what you need to have is some numerical kind of, I suppose, vector, which says, what is the relation of our inputs to our output? And in most of the cases, let's say an image classification task, the output is going to be a prediction whether it's class A, B, or C. And so what our output would be a vector which gives us, or a one-dimensional matrix, which gives us a probability score that the output is related to, this is what we'd wish to have, related to the specific class. So it may be class A would be 90%, 0.9, class B would 0.4, and class C would 0.1. Now, to achieve that, what we need to do is use these things called activation functions, and typically we used a specific activation function to do that. We're going to talk about that in a minute, how we get to that part, but there are unique properties of this activation function which allows us to build those probability matrices based on the inputs, which is super important because we need to use that to be able to do some interpretation and reweighting of our outputs. So moving on to the probably most important part of a neural network is this activation function. And remember I said at the very beginning, if you have inputs and you have an output, we need to be able to do some transformation, and we need to allow us to do nonlinear transform, or we want to introduce nonlinear transformations into the network. And the reason why that is because what we're trying to do, when we have all the inputs, we need to have an output which is a sum, which effectively sums to 1, because we're trying to work within that range. You could do it in a different way, but this is just the standard approach that we take. And what we try and do is we use these different activation functions to introduce this nonlinear approach. So sigmoid, for instance, 1 clips at infinity, positive and negative infinity in this sense, but it's at 1 and 0. There's challenges with that, but we use it for certain functions depending on if you're looking to do to reduce the amount of feature space and overfitting of certain neurons. We don't have to worry about that. I just want to introduce there are different types of functions, and the one you'll probably hear most commonly is this thing called the ReLU function, and the ReLU function is a fancy way of saying rectified linear activation function, and it's become a common approach because typically what happens when you are training a neural network, the process of forward pass, that process of going from the inputs to building to the final output and then readjusting the weights on the backward pass, you run the risk, if you have that function which you see on the top right that says sigmoid, you run the risk of going into the space where it starts clipping very quickly. And what do I mean by clipping? It saturates at either 1 or 0. And when that happens, and the process of that happening is maybe because of the rate at which you are doing your learning. So there's a process, as you can see, you have to start unpacking many things here, but there's a process of when you're learning, you're effectively trying to do some differentiation, looking at the angle at which the steepness of your slope is changing. And potentially if you're learning too fast and the jumps that you have between one angle on the line and another angle on a graph line, you end up hitting like a specific local minima, or potentially a point where you don't realize it's not the lowest or highest. And that can also be affected by that clipping or the saturation which happens in the sigmoid function. So as a way to avoid that, the ReLU function says, hey, you know what we'll do? Rather than confining it to a small domain, a small numerical domain, which is between 0 and 1 in this case, we will give the ability to go from 0 upwards. So we can keep going to infinity, and there's no clipping occurring. This gives us a larger space and allows or reduces the chances of saturations within the nodes. Because what happens when you saturate at a specific point, you end up losing the ability for that node to provide you any insight or to provide the ability to encode any knowledge within that node working. So it's important that we don't clip. And probably some of you are looking at that graph of the ReLU and saying, hey, but it stops at 0 and it starts clipping again, or it starts saturating at 0. Yes, that's correct. And this is a kind of a common problem that we see. So there is another version, flavor of the ReLU function called the leaky ReLU. And rather than it's clipping, I don't know if you can see my mouse going flat, it actually has a slow gradient which goes below 0. So that allows it to overcome, compensate the problem with it clipping. So these are the activation functions. And one of the specific ones which is used for your final output layer is this softmax function. So if anyone's done logistic regression, I'm sure some of you have seen the logistic regression or logistic curve. So what sorry, just having a drink. So if you've heard of the logic, effectively, the softmax functions allows us to use the logic function to predict based on a threshold which class or which effectively class this input relates to for the output. There's a lot of hidden math behind the scenes to achieve this, but I would recommend doing some further reading if you want to understand how the logistic regression or the softmax function works. But it is a way to predict based on the value of that that curve, the point on the curve, where the which class probability it most relates to. So remember, when you have an output of a multi-class classification, in most cases it's if anyone has the background to machine learning, you do one versus many. So you're comparing one output to all the other classes, and you do some segmentation on the graph. It allows you to use softmax, or the logistic function is a way to give you the confidence score of each of those classes. There are other ways to build neural network final layers. For instance, you can use an SVM approach, a kernel-based model, to determine which class it's related to, but those typically have some weaknesses when it comes to overfitting because of large feature spaces. We don't need to go into that today, but I just want to give you the output on that one. So finally, or a few more layers to go. Hope everyone's taking notes at this point, and everyone's still awake. Hopefully no one's too bored at the second, but we've got a few more layers, which is important to think about. It is the regularization. Now, for any traditional machine learning experts here or practitioners, regularization works in the same way or very similar to your standard parameterized models where you penalize coefficients. You can apply both L1 and L2, and they work in the same way in terms of drawing down to 0. But the way we implement it in neural networks is by introducing things like dropout layers or batch normalization. And things like dropout layers allows, so let me just give a little bit of background to this. So regularization, for those that haven't heard about it, if we take the scenario where a model fits very, very well to the data, like nearly 100%, let's say, potentially what we can actually be introducing is a lot of overfitting into the model. So regularization, what it does, if you looked at it from a layman's perspective, it reduces the ability, the accuracy of the model's predictions. And it does that by penalizing coefficients within your model's function. Don't worry about too much of that, but effectively what it means, it reduces the ability for it to fit very well to those data sources. But what it does, in turn, it introduces generalizability. So it introduces the ability to generalize beyond the data which you're predicting about. And that's super important because you don't want to always build a model which can only predict on the data that it knows and can't do anything outside of that data set. You want to be able to predict on data sets that the model has never seen before. And that's what you do with with regularization. And there's different breeds, different types of it, and different approaches to doing it. And then in a neural network, one of the approaches which was introduced was this idea of a dropout layer. And all the dropout layer does is it identifies randomly or potentially based on node exploration and interpretation, the nodes which could, if you know about the nodes, or randomly nodes which are causing gradients to be incorrect. And then all we do is that we shut those nodes down by making the inputs and outputs 0. So no longer do those nodes work in the network. They don't produce any data, so they don't do anything. And this introduces the ability, or the ability for the model to have more generalizability, across a broader set of data. Super important, because this is used a lot in computer vision. And finally, there's one more, which was introduced not too long ago, and we're going to hear about that actually, about 2015, 14 time, is this idea of batch normalization. And it's all about how do you take the inputs and do some normalization against the broader set of inputs within that layer in the network to be able to normalize it. And that way it actually standardizes the output of a node and reduces the chances of that layer causing overfitting. A little bit more complicated than that, but you can see from here, it makes the kind of a lot easier to initialize weights within the network when you first start off that cold start problem of having the first initialization of weights. So we've gone through them now. We've gone from activation functions to inputs to a fully collected layer and variety of different layers to reduce the size of the network and also to reduce the chances of overfitting. And at the very end, we end up with this odd-looking bird on the left-hand side, which is an image, and it's doing some convolutions and introducing nonlinearity, to some pooling functions, to then some mappings on those vector spaces, and then finally to some predicted values for each of the classes. Remember, those classes, the network doesn't know that it's a bird, a sunset, a dog, or a cat. It doesn't know anything like that. All it knows is that based on the vector space that you've introduced at the very beginning, that it could represent that class A, which is p-bird, a probability of bird. It doesn't know it's a bird. So that's effectively from left to right, the full neural network, which represents the same things I showed you at the very beginning of that neural network. Not too bad in 40 minutes. And I think hopefully it gives you a little bit of understanding. So let's talk about a little bit more in practice. So one of the things that's super important, if anyone's familiar with playing with neural networks or training neural networks, it's super intensive. It takes a lot of time and a lot of resources. Which was one of the reasons why, in the 1930s all the way up to 2010, it was quite difficult to use neural networks to do anything because we didn't have the compute and we didn't really have the kind of capacity to store the amount of data that we needed to process. I heard, for those who didn't hear earlier, Rick, we were talking about home working, and Rick was mentioning that he's going to be picking up his GPU from the office and taking it home with him. So we're going to talk about that in a bit. But one of the key things here is how do we process and how do we train our networks? Well, the more compute power, potentially the more GPUs, so the graphics processing units on those graphics cards that we have in our computers, the faster it will be to do some training. And one of the kind of recent things which now people are doing a lot with is using GPUs like the ones available in the P3DNs, the EC2 instances in AWS, to do training for neural networks. And that's been one of the most critical turning points for neural network training, has been the ability to harness the kind of multi-CPU or multi-GPU cores available on these graphics cards to do training. And some of the most important things when we're building these models is not only the training speeds is improved by computational power, but the way we build our parameters, our hyperparameters. Hyperparameters in this sense are, the specific settings that we use to train a neural network, such as the learning rate or the size of that kernel that we mentioned before, as well as the architectures. Now, very shallow architectures, they don't take very long to learn, but they probably can't encode that much information. but very steep architectures can code a lot of information, have a very large parameter space, but potentially take a very long time to train and have the tendency to overfit if you don't have the right type of data. So one other thing which is super important, which no one really talks too much about, is data augmentation. Now, data augmentation is a very simple technique, but has an extremely powerful outcome in any neural network training scenario. I say any, I say majority, caveat on that. So data augmentation, and there's the Doge again appeared in front of you, is the process of taking your original data set and doing augmentations on the data. If it's images, it may be rotations and skewing and changing the color and shifting and doing translation, or it may be things like if it's text, it may be doing the adding words, removing words, changing sentence structures, many permutations of the sentence. There may be many different things that you can do with it. But these are super important because what you want the model to do, especially if you have a very limited data set, is be able to understand the data in different ways based on different structures that it sees. So that image that it sees, although we see the image of the dog in 4 different ways being the same dog, if you take the numerical representation underpinning that image that the computer is representing, that metric space, that metric values that we'll see, the matrices, are very different in each one. Because remember, the matrices represent the colors, represent the depth, represent many different things around that image. So if we're doing rotations, now the image has more, the models have more data to be able to be interpreting with. So that's super important. So we do these different types of data augmentations to improve our model's generalizability. Finally, I just want to say at the bottom here, we're going to hear about transfer learning. I'm going to talk about it in a bit. But effectively, transfer learning is a technique to take very large pre-trained models, which have been trained, maybe on a lot of infrastructure and a lot of over a long duration of time with existing data sets, to give you a base model to be able to do different types of tasks. Now, I've got some slides in here to talk about that later, but in case we don't have enough time, I see we're already at 44 minutes. Transfer learning, it has different types of applications, but it all depends on the type of domain and tasks that you're trying to apply it to. So if you train a model which can interpret dogs and cats, and then you're trying to use that model to interpret cars or houses, it's probably not going to be applicable. So you've got to know the domain, the target, so your source and your target, and then you've got to also know the type of task which you're trying to apply for. Okay, so with that being said, a little bit of insight into computer vision, the backgrounds and how it constructs. I just want to run through a few developments in computer vision to get you the up-to-speed understanding of where we are. So around 2012, CNNs were, well, before 2012, let's look at it another way. Computer vision wasn't very good. There were very few models, or there was no models that could achieve a very good accuracy. And there's this standard measure of accuracy, which is, or challenge, which is run every year. The ILSVRC, which is effectively image classification task using the ImageNet dataset. An ImageNet dataset is millions and millions of images, and the test effectively what it does, it looks at the error in predicting the class label of those images out of a random subset of images in that ImageNet dataset. Human accuracy of predicting the object or the thing that's in the image is around 3 to 4%. Before 2012, there was around 25 to 35% error in being able to select those top 5 images. So pretty bad, to be honest. Then came 2012, and a few now very well-prominent researchers, Hinton and his PhD students, came along with this network called the AlexNet architecture, which achieved a 15.4% accuracy or error rate, which is pretty phenomenal, given that the best next in class was 25%. And it all came from their implementation of using this convolutional approach to building neural networks. At the time, it took around 2 weeks to train this network over the ImageNet dataset, and it was done on a desktop underneath the researcher's desk. So pretty phenomenal at that time. Since then, there has been a lot of developments, and 2014, so 2 years on, a new network came along with a 19-layer network with a very small kernel, and it used many layers of convolutions to achieve, encode a lot of information. And by doing so, they reduced the amount of error from 15 to 7.3. So now we're starting to get close to human accuracy, okay? So human error and human accuracy. Suddenly, GoogleNet came along and said, hey, we've got another approach to do this, the inception model. So if anyone was a Caffe machine learning framework enthusiast back at the time, they've probably seen a lot of inception and GoogleNet models available on the Caffe Zoo libraries. It's a very good network, but it takes a different approach. It doesn't go so deep, but it uses a lot of parallel convolutions to do a lot of encoding. And they brought that error rate down to 6.7. And then pretty much the most famous one, which we're all driving, or many of our models are now driven by, is this concept of the residual block, which comes from the ResNet. So Microsoft in 2015 produced the 152-layer ResNet, which took a very long time to train. I can't remember the exact figures, but it was, even though it was on a large amount of compute resources, it took a while to train. But as a result, it achieved an accuracy or an error rate of 3.6. And as you can see on those slides, humans are in the range between 5 and 10. I think the average human is like 4.8 to 6 point something, but they widen the range based on certain criteria. So suddenly we've now gone from 2012 in 3 years to 2015, a point where neural networks are producing for very narrow tasks. Remember, I want to always emphasize this. This is a narrow task. It's predicting based on data that it knows around, and a very simple task of, is this a cat or a dog? Obviously, it's not cat or dog, but it's a wider set of labels, 80 labels, I believe. An error rate which is less than a human being, which is phenomenal. And there hasn't been that much progress in many domains for a long amount of time. So it's an incredible feat what's happened in the last kind of 5 to 10 years, effectively. So since then, there's been a lot of work, and not only a lot of work in developing the underlying infrastructure or architectures to do this, but also the types of tasks which a neural network can do. Now, one of the things which has been really important is the ability to not only say, is this a dog or a cat, but say, hey, what's in this image? Where do they sit? And can we label it? And can we build bounding boxes? And can we see interactions between things? So there's been a lot of work in this area called regional CNNs. If anyone's seen this thing called a mask RNN or fast RNNs or faster RNNs, they're all kind of sitting in the flavor of object detection with boundary boxes. Now, one of the infrastructures which I think is, or architectures I think is pretty decent and very useful to doing different types of object detection, is this thing called the You Only Look Once. So now whenever you hear YOLO, or hopefully you don't think of you only live once, you think of computer vision. Hopefully that's changed your vision for life, but hey. And comparing it to other approaches, the simple architecture which they use means that you can effectively process images in real time. Now, if you abstract away from what a video and an image is, they're the same thing. Effectively, an image and a video, or a video is just an image with lots of images stitched together. So if you can run your inferencing fast enough, you can suddenly do real-time prediction of objects within videos. Ta-da, you've suddenly got a video object detection framework. Really awesome stuff. I would definitely recommend you to go and explore this a little bit more. Given we're short of time, I'm not going to speak too much about this architecture, but it's something that's really driving this. And there's different types of YOLO architectures as well. There's a light version which you can deploy on a smaller compute resource. So you effectively train off and then just deploy a very lightweight model which can do kind of inferencing at the edge. So some really cool stuff there. Okay, so I did say I was going to talk about
Yeah, go for it. Those YOLO models, if they're run on a video, then aren't you only using the information in a single frame? Are there any extensions that would use the history of frames?
Sure. So so the model itself, well, the way the model is built, it abstracts away from encoding information across scenes. But what one can do is you start to build a ensemble-based approach where you don't only just use YOLO, but you can use something like an RNN or a LSTM to encode information from previous scene information. So it gets quite complicated and quite hairy, but it's quite a nice. There is some research papers on this. Is like, how do you encode temporal information in videos by using a combination of neural network infrastructure architectures. Hopefully, I can talk to you maybe offline about that a little bit more. If that answers your question, no worries. Okay, so moving on. So that's I want to bring you all the way here. So, you know, this is like the cutting edge now. This is like getting into really research space where there's a lot of work going on with industry and academic partners kind of in many different parts of the world to develop that object recognition architectures. So finally, I did say I'll touch upon transfer learning. And I'm not going to spend too much time, but there are different types of transfer learning for different types of tasks. Typically, they are trained based on pre-existing kind of very robust or large data sets like SQuAD, which is for question answering, COCO, which is more about annotations. So, you know, where do objects sit within an image? So you have bounding boxes. A lot of work went into that to create that data set. And ImageNet, which is probably the most famous, which is used for the kind of early eras of computer vision models. Based on that, you can do different types of tasks, but it's important to know that not all tasks can be used within a transfer learning methodology. As I said, depending on the domain, at the source and the target, you should or you should not use transfer learning. And depending on the type of task that you're trying to train, are you trying to train it on one type of task and transfer it to a new type, this forward transfer? Are you trying to train it on many tasks? So, you know, tell me about houses, tell me about dogs and cats, tell me about furniture, and then use that to do another task? Or are you trying to use meta learning? So you've learned about something, but you're using those parameters, whether it be autonomous, and this is a lot in the space of autonomous driving and kind of reinforcement learning space, is to learn meta about a task, whether it be, you know, robotics, how an arm moves, and then use that in another context. Each one of those has its own challenges, and there's a very active area of research. I'm not going to go into this graph. This is kind of like a workflow on the types of tasks that you're trying to achieve. Sorry for the resolution on that one. I'll update that. But let me just move to this one. One of the important things which goes back to that thing is negative transfer. Now, negative transfer is this process of, hey, if you've got a source and you've got a target that you're trying to achieve for the transfer learning process, the problem is if those two are not compatible with each other, if the model has got encodings for the source which doesn't align with the type of task which is to be achieved by the target, then you end up in this process called negative transfer. Now, I put this in here because if there's anyone thinking about you know, learning or pursuing further education in new topics and are interested in kind of neural networks and in this space and feel like it might be quite saturated, this is a really hot topic which people haven't really started to develop in too much. So if you're thinking about pursuing a PhD or a master's topic and you're on this call, chat with me and I can have a little bit more of a discussion about, hey, you could shape a research question around this one. That's just my take on reading the literature in this space in a minute. So hopefully that might be you know, spark your interest. Okay, so gone through all the journeys of how architectures develop. Now, guys, I'm just going to quick ask to the crowd. We're at 4 minutes 18. I haven't yet covered, as I said, this is like a 2-hour talk usually. I haven't yet covered AWS services. Would you like me to continue down the theory, and we can save the AWS services for another session? Or do you want me to dive a little bit into the AWS services and give you a quick overview of SageMaker? What would you like? as I want to make this as interactive as possible. Or are you all enjoying the theory and thinking, wow, I'm learning something from HISS?
On the chat, we're seeing everyone saying theory. Theory, please. All the theory. Feed us more theory.
All right. Like okay, I'll keep going. Looks like people like theory. I never thought that. I used to do academic lectures, and I think by halfway through, everyone would be like, hey, I hate this theory stuff. So, okay, this is good. So finally, so we've built our models, we've looked at architectures, we understood that, you have different types of architecture, different types of layers, but hey, that's all well and good, but how do you actually measure this? How do you compete in something like that ImageNet challenge every year? Well, I'm going to show you a few different metrics which are used for measuring performance of models, and then apply that into the world of computer vision. So if anyone's had a background or played with machine learning before, they've probably heard this buzzword of, hey, PNR or precision recall or AUC curves, ROC. They are all different metrics to measure how well the model, the outputs of the predictions compare to the actual values of the data itself. Like I said, we're working in the space here of supervised machine learning, not unsupervised. We don't even want to talk about that today because it's another 4 hours, and I don't think you've got till sort of 2 a.m. tomorrow morning. So if we think about performance, what we need to do is measure what we actually get in a prediction with our actual values. And there are, based on the type of supervised learning, is it regression or classification? Regression typically is numerical discrete values, let's say. So it'll be, we want the value of 6, but we produce 7. What is that? What is the delta between the 6 and the 7? Maybe it's not 6 and 7. I'm just giving you some arbitrary values. But then we can use some square error or some measure of error between those two numerical values. But another way of doing it is if we're predicting labels, if we're predicting, is it a dog, is it a cat, is it class A, is it class B? We need a thing where we can look at the true value, which is a dog, and our predicted value, which is a cat, and turn that into a measure of accuracy, which is effectively precision, measures how accurate is your predictions. So the percentage of your predictions which are totally correct, and in a formula that is true positives divided by true positives and false positives. And then recall is that how good is your model at finding those positives. So it's super important to understand the nuances here, because for different types of use cases and scenarios where you apply machine learning workloads to a domain, it may be important to have a very high precision or important to have a very high recall. Now, for instance, if you have models when you're trying to do outlier detection, your aim here where potentially there's only a few labels which have the class, so it's very unbalanced. 99% of the data is for one class and 1% is for another. You want to be able to build a high recall, because it's going to predict really well. Your predictions and your precision is going to be really well because it's going to be skewed by that one class. So because the majority of those labels are in that one class, it's always, it's going to predict very well. However, if you were doing fraud detection and you had a very small amount of fraud cases or spam cases or whatever it may be, you need to ensure that you examine the right metric for the right domain. So if anyone's ever read research papers or read some medium.com articles or some other third-party venue and seen some metrics which have been, spewed out saying, hey, this is 99% precision, I always recommend you to go and look at a little bit more depth and say, actually, let's have a look at what that actually means. And this is probably very good to do, and it's good common exercise to do every time you read papers that are reporting their precision scores or their recall scores. So why this is important? Because precision recall is a way to tell some level of accuracy for and recall for each of the labels within our model. So in here you see this thing that says false and true. They are actually just label names. So is it the false class or the true class? Is it a dog? Is it a cat? Is it a table? Is it a speaker? Whatever it may be, they're just different class labels. In our case, when you're doing computer vision, depending on the number of classes, you're going to have different number of rows in this table. But what you always notice is that the values add up to 1 because it's a probability. And the other thing you need to know is that every time you build a prediction, you're going to have a confidence score for each time that prediction is created. If anyone's done scikit-learn in the past, you know you can do you can get the confidence score alongside the actual class label that it predicts. That's super important because you need to get those values to determine, if you go a little bit further back into the theory of this, you can look at your confidence intervals and determine what is the range of error that you're creating when you're building your predictions. So that's a little bit more detailed. You probably don't need to know that, but this is how this is all generated in the background. So that's one metric, precision recall. Keep that in your head, because the next one we need to think about when we're doing computer vision, especially if we're doing something like object detection, is how well does the model predict the bounding box against the ground truths bounding box. And that metric is called the intersection over union. And very simple, it's not complicated at all. If I have a data set and I have annotations which has the ground truth where it knows it's x1, y1, x2, y2, and those are just the edges on my polygon, which is my bounding box. In this case, we're taking a polygon to be some rectangle. Then our prediction is going to predict where those edges are on the predicted polygon. And all our area over the union is looking at what is the difference between the two polygons. So that space within that square of the overlap, and then turn that into a percentage. Is it 1, it would be completely over it. If it was 0, it's completely apart from each other. There's no overlap. That's all it is. So now you've got precision recall, and suddenly you've got an intersect value. We can create this thing called the average precision, the AP. Now, anyone that's looked at research papers in this space, looked at towards data science or some other kind of online tutorials, you might see, hey, the COCO data set with the MAP of 94. And what does that mean? So average precision just combines precision recall as well as some the intersect over union to be able to build a representation or a comparable metric between two different object detection models. And we're going to see how that works, but effectively the formal definition is the AP summarizes the shape of the precision recall curve, and we're going to work out how we calculate that, as is defined as the mean precision at a set of equal spaced recall levels. So those recall levels in this case are a subset or a set between 0 and 1, but it doesn't have to be that. It can be a different spacing and different intervals segments, but that's dependent on the type of test you're trying to run. And when we calculate AP, we probably calculate it at different points where the intersect occurs. So maybe your AP is calculated at 25% of when the intersect, the IOU, occurs at 25% or more, or maybe you want a very precise AP score when it is AP 95 or more. So that means 95% of the inferencing or the predictions have a score of 95% more on the IOU. So what does that actually look like when we try and interpret that? So to do that, you're never going to do this by hand, but it's probably good to understand what's happening. What we do is we build our model, we train it, we get all our data, and we've done everything right. Now we try and predict. We predict on a set of data points, and each of those data points have its own confidence score, which I mentioned before. So what you do then, you rank each of your predictions based from the highest confidence score all the way down to the lowest. And for each one of those scores, you build the precision recall number or the precision recall metric for each one of those confidence scores. As we see here, if we take row 4, the precision is the proportion of true positives. So what we do is we do 2. So we know there's 2 true and there's 4 in total that's been taken place so far. So then it's 0.5, and the recall is the proportion of true positives from the population of total positives. Well, we know there's 5 total positives in our data set. So, and since row 4, there's only had 2 that's happened, then our recall is now 2 over 5, which is 0.4. So we build this kind of table of precision recall scores based on the decreasing value in confidence score. And what we end up, if we plot this, of the precision recall curve, is this precision recall staggered effect. So as the precision goes down, we see this jumping effect across, as the recall goes up, what we end up with this jumping, fluttering effect within the precision score. Now, for the mathematicians out there, we can build a smooth polynomial to calculate the integral underneath this curve. If you've ever done math before or played with integrals, to get the area under a curve is effectively the integration of that curve. And what we can do is, once we take that value, we get a single numerical value, which is our AP score. And that single numerical value, which I'd show you here, that's the smoothing effect. That single numerical value gives us the ability to now compare the 2 different models. Even if they're working on 2 different tasks, we can compare now the precision based on a standardized measure, which is AP. So for anyone has seen something like the COCO dataset and models being trained on the COCO dataset, we're now hopefully familiar with how the AP score and the IOU relates to its measure when you're trying to compare 2 different models. Just to say, in the context of average precision and mean average precision, it makes no difference. It's just a terminology which is interchangeable and effectively got introduced by the COCO researchers which talk about the COCO dataset. So you can use those interchangeably.
So I just want to wrap things up here now. I want to thank you for the last hour, hearing me speak about computer vision and going through the history and some of the techniques which are being used. I know we covered a lot of content, from the basics of neural networks to how we can build convolutional neural networks, and then the advancements in architectures and how do we measure that. Hopefully you've learned enough content to apply this to your day-to-day activities, and look forward to providing some more content on additional computer vision topics going forward in the future.